Hi class, we are starting chapter 5, which is on determinants. So this first section, 5.1, we are going to discuss what a determinant is, some of its uses, mainly just how to find a determinant. So there's actually a few ways, depending on the size of your matrix. So let's talk about that. So determinants only exist for square matrices, okay? If we do not have a square matrix, we cannot find the determinant of a matrix. So there's many ways of finding a determinant, and again, the method that you use depends on the size of your matrix, okay? The size of the matrix and the values that are present are going to help you choose which method is best for deciding what the determinant is and the method that you're going to use, right? So if I have a 1-by-1 matrix, so just a matrix with a single entry, right? So let's say that A is just the value of A. Well, then our determinant, which is signified by DET with the matrix on the inside, so the determinant is a function, okay? And it's given by what looks like absolute value of A, okay? However, this is not absolute value, okay? It's like a matrix, but without the brackets, right? And so if we just have a single value for A, then the determinant of that matrix is just that value, okay? So again, this is not absolute value. It is a notation. If we have a 2-by-2 matrix, right? Maybe that looks like this, A, B, C, D. So these are just general values here. Then the way that you find the determinant of a 2-by-2 matrix is that you multiply the diagonals and you subtract them from each other. Okay, we're actually a little familiar with this from the inverse of a matrix. So A times D minus B times C. Okay, so again, the notation is what looks like an absolute value for our matrix. Okay, so again, this is not absolute value. It is a matrix notation. It's actually the notation for the determinant. And so the way that we find it for a 2-by-2, again, as I said, is just the first main diagonal, A times D, minus the secondary diagonal, the opposite diagonal, I should say, which is B times C. Okay. If we have a 3-by-3 matrix, we have a generalized formula for that as well, right? So here we have 3 entries across, 3 entries down, right? So my rows and my columns. Then the determinant of this, given by the straight line brackets, okay, is going to be, so I'm going to show you how you do this. So the way that I prefer to do this is by taking your matrix, right, A, B, C, D, E, F, G, H, I, and then you repeat the first column, and then you repeat the second column, okay? So you take your regular matrix, and then repeat the first and second columns only, okay? And then what you do is you go this way and you multiply. You go this way and you multiply, and you go this way and you multiply. And you add them together, okay? So A times E times I, and then I'm going to add that to B times F times G. I'm going to add that to this diagonal, C times D times H. So notice, the way that you know you're using the right diagonal is that it's the only diagonals across, right, from the upper left to the lower right that has 3 entries. 3 entries, 3 entries, 3 entries. Okay, so going this way, and you add those products. Then you're going to subtract from that, going the opposite way, just like you did here, right? You did this diagonal minus this diagonal. So here we're doing all of these diagonals, and we're going to subtract from it the products of these diagonals. So I'm going to subtract GEC, I'm going to subtract HFA, and I'm going to subtract IDB. This method does not work past n equals 3. So for instance, if I have a 4-by-4 matrix, this method does not work anymore. Okay, I'm sure that there is some sort of an adjustment to this method that you could use for higher level matrices, but this algorithm that works for, sort of the n equals 2, and then expanded for n equals 3 does not work for n equals 4, 5, 6, etc., etc. We'll talk about how to do higher order matrices in this chapter, but for right now, we don't have that. Okay. So another way of looking at this, right? So this is from your book, is you're taking your matrix entries, you're repeating the first and second columns, and then you draw your diagonal. So the thing that I use to write your notations here, it does not let me strike through an entire diagonal. So that's why I had to like show you with the cursor what this does. So that's why I included this picture that has the strike throughs all the way through, right? So you're doing this first strike through, you're multiplying these products, and then you're adding them, right? So all of these are positive, and all of the ones this way are negative. Okay. So again, there's another method that we use for the higher order matrices, and this method works for 3 by 3 and larger matrices, and it's called cofactor expansion. We'll get into that in just a second, but first let's do some concrete examples of n equals 1, 2, and 3 using these methods, and then we will get into this cofactor expansion method for higher order matrices. Okay, so let's take a standard example for n equals 1. Let's say that A is a single matrix, it has a single entry, -2. Then the determinant of A, given by the straight brackets of -2, it is not the absolute value, it is just the value on the inside. So the determinant here for a single entry matrix is just that single entry. Okay. If I have n equals 2, let's say it's 1, 2, 3, 4, just to keep it simple, okay, I'm going to do this diagonal, and I'm going to subtract this diagonal. So that's going to be 4 minus 6, which is also going to get me -2 in this case. Right? Let's take a regular 3 by 3 matrix. Okay, so let's take this one. So again, remember what I'm going to do. I'm going to rewrite this matrix. I'm going to have my first 3 columns, and then my 4th column is going to be this one, and my 5th column is going to be this one. So I'm just going to repeat the first 2 columns at the end of my matrix. Okay, so the determinant of this, which is given by straight brackets. So if I ever say straight bracket and then a matrix on the inside, you should know that that means find the determinant. I am not giving you a matrix, I'm asking you to find the determinant of a matrix. So what I mean is, if I were to give you as a problem only this right hand side, you should be aware that that means you have to do something to this matrix. It does not mean just, hey, here's this thing, right? It means that you should be coming out with a singular value. So notice that when you find the determinant is always a real value. You're coming out with a single value in these cases, right? I'm getting a number. When I find the determinant here, I will get out a number, okay? So when I do this again, I write my 3 columns, and then I repeat my first 2 columns to make the 4th and 5th columns, right? 1, 2, 3, and then 4 and 5 is just me repeating 1 and 2 and taking them and putting them at the end. So when I do this, I'm going to have first 3 plus 2, and this will get me 0, right? 3 plus 2 plus 0. 1 times 1 is 3. 1 times 2 times 1 is 1. I'm sorry, 2. And then there's a 0 here, so it's 0. For the subtraction, I'm going to have a -1, so minus a -1, minus a 2, minus a 3. I'm sorry, minus a 0. Apologies. Right? 0. So when I add these all up, okay, I'm going to get 3 plus 2 plus 1 minus 2. So that's really 3 plus 1 is 4. Right? So it's actually very quick to find a determinant for a 3 by 3 using this method. This is my preferred method. Generally, this is what I'm going to show you when I do this. However, this cofactor expansion, it can be kind of difficult to understand at first until you do a couple of examples. But cofactor expansion, when you're used to it, when you're familiar with how it works, actually goes very fast also. So cofactor expansion, if you are taking Calc 3 or have taken Calc 3, cofactor expansion is the method in which you find determinants in Calculus 3. it is also the method in which you determine the cross product. So we had a proof where we're talking about linear transformations for cross products. The way that you find the cross product is actually by calculating a determinant. Okay, it's a little bit more involved in that. We're not really going to go into it. When you take Calc 3, you will talk about how to find cross products, and it'll be by cofactor expansion. So you'll see that there in that class. We've talked about cross product a little bit. You know, the nitty gritty of cross product is in Calc 3. That's not the real purpose of this class. Okay. So let's talk about cofactor expansion. So cofactor expansion has a couple of important pieces that we'll need to discuss in one at a time before we put it all together. So we have what's called row expansion, we have column expansion, and we have our companion matrix as well, and minors, right? So we're going to talk about those four things, those 3 or 4 things, one at a time, and then put them together so that we can talk about cofactor expansion. Okay. So cofactors are denoted as C sub ij, where ij is the row and column, right? Just like when we have A sub ij, it's the same thing. So each entry in a matrix actually has its own cofactor. Okay. They have alternating signs, and signs alternate according to their position, and we have what's called the companion matrix to kind of help us understand what the sign is supposed to be. It goes by a pattern. The sign factor for each cofactor is -1 to the power of I plus j. So remember, I plus j is the row you're in and the column. So your -1 is raised to the power of the row number plus the column number. Okay, so you add those two things together, multiply that by -1. So remember, what does -1 to any power do? If it's even, the -1 to an even power is a positive number, right? If -1 is raised to an odd number, then it's negative. So really what these things do is they alternate in sign from positive to negative. Okay. You should have saw a problem like this in your exam, actually, for those of you who are taking my fall semester, 2020. There's a problem like that as well, in that we're using these ij terms, right? So what we're going to do is we're going to use the following associated sign matrix, what we call the companion matrix. That's going to help us determine what the sign is for the cofactor expansion. So really what happens is you just alternate in sign from plus minus, starting with pluses, because what is your entry here? This is C11. So you're going to have -1 raised to the power of 1 plus 1, which is 2. So you're going to get a positive. The next one will be 1, 2, which is -1 to the third power, which is odd, which is going to be negative. 2, 2, or 1, 3, which is 4. So -1 to the fourth power, -1 to the fifth power, -1 to the sixth. You're going to alternate in sign. Same thing as you go down, you're going to alternate in sign, right? So this matrix will always be the sign of the multiple that you're using for your cofactor. Okay, so you just alternate in sign is really the easiest thing, where this is positive, the negative, the positive, the negatives, and so forth. So notice that the main diagonals are always positive, so your row entries also alternate positive and negative for the first entry in the rows. Okay, so we want to choose a row or a column to go down. We go down either a row, or we can choose a column, and we can actually choose any row or any column. Okay, so generally we choose the one that has the most zeros, because we're going to be doing a lot of multiplication here, and so when you have a lot of zeros, things multiply to 0, right? So it's always, you always want to choose the row or column that has the most zeros. If there's not a lot of zeros, choose the one that has a lot of ones. If there's not a lot of ones, choose the ones that have easier numbers to work with. 2s are easy, right? You definitely don't want to choose the row or column that has like -2 13 on it, right? Some number that's not easy to multiply by. Okay, so you always want to choose the row or column that has the nicest numbers, basically. Okay, and as we go down a row or column, depending on which one we're doing, and again, it's on you. You can go down a row or a column, and you can go down any row or column. Okay, as we go down that, we're going to take the entry that we start with in that row or column, and we're going to go down each one. Okay, and it's going to multiply against your cofactor sign, right? And times what's called the minor. Okay, so the entire cofactor is a sign, this plus or minus here, right? And what's called the minor, right? And so as we're going, we take our value, okay, and wherever that value is, that entire row, the entire row and the entire column goes away, and we make a sub matrix with the entries that are left. So if I took away this entire row and this entire column, all the entries that are left would make up a sub matrix. I would find the determinant of that sub matrix, and that would be my minor. Okay, so we call the minor, even though it's minor and not major, right? It's a large M. Large M ij, because your minor also determines on what entry you're at in your matrix. Okay, so I know all this probably sounds confusing right now, but once we do some examples, it'll be much, much easier to follow. Okay, so the determinant of this remaining matrix, okay, is your minor. So your entire cofactor is given by this. So for this entry, okay, my cofactor is given by the sign of the companion matrix, which is this matrix, okay, times the minor, which means that I take this entry and I delete its column, I delete its row, and all the rest of the entries that are there, I find the determinant for, and that's the minor. So I'm finding the minor, the little submatrix that's left, and I'm multiplying it times the factor of my companion matrix entry. Okay. So the determinant of A is the sum of each entry times its cofactor. Okay. So if I'm going down a row, okay, if I decide to go down a row, then I'm choosing I, right? Because I, remember, I's are rows, J's are column. Rows first, columns first. So as I go down this row, I'm choosing a different I value each time. Actually, I think this should be J, because if I'm going down the row, the J's are changing as I go down the row. But that's fine. So I'm going to have my cofactor value times the value I'm at in the row, and then the minor that's associated with each entry. And if I'm going down a column, it's going to be the same thing. So again, I think that these two values should be swapped, but as you notice, there's really no difference. The only difference is, am I choosing I to change to N, or am I choosing J's to change to N? And so these two formulas should be switched. This formula should be a column expansion. This should be a row expansion. But to be honest, I figure most of you guys are looking at this and are probably saying, what the hell? I don't understand this anyways, which is fine. We're going to do the example. When we go from the example, that will make more sense than the formulas, right? The formulas always trip people up, especially summations. So let's go ahead and do some examples, okay? So we're going to use our example, our n equals 3 example, which we did already, which was this one, okay? So remember we found the determinant here already by using the method that I like, which is replacing, taking your matrix, taking the first two columns and throwing them at the end, and then doing our diagonal multiplication, adding some, subtracting some, right? So these ones, this way gets added, this way gets subtracted, okay? And that's fine. So now you might be saying, well, Professor Williams, why are we doing this example again if we already did it, you know, besides just showing you that it works? This cofactor expansion, remember, works for matrices that are 3 and larger. I only showed you the fast way for finding determinants up to size 3 by 3. Anything larger than this, you have to use cofactor expansion. So we're going to show how to do cofactor expansion on something easy that we've already got the answer to, right? So that's why we're doing this one again. So let's take this matrix that we have here. So the first thing I gotta do is I gotta figure out what row or what column do I want to go down. Okay, I can go down this column, this column, this column. I can go down this row, or this row. Now, it doesn't matter which one I choose, but I gotta go down the entire row or entire column. I'm gonna get the same answer out. The determinant does not change depending on the row or column I choose. The determinant of a matrix is always the same value, period. It does not change in value depending on how I decide to calculate it. You're only going to get one value out, okay? So I definitely want to choose a row or column that has zeros. So this column has zeros. This row has zeros. So I can choose anyone, but I can choose one of those two will be easier for me. Because I'm multiplying a bunch of stuff, I'm adding a bunch of stuff. So you always want to choose the row or column that has zeros. So now the next question comes, now that I have a zero, right? This column has a zero and this row has a zero. Should I go this column? Should I go this row or should I go this column? Well, this row has a 1 and a 2. This column has 1 and 1. All ones are always better multiplication-wise than choosing a 1 and a 2, right? If I have a 2 here and I have to end up multiplying stuff by 2, that's not a lot harder, but it's harder than multiplying stuff by 1s, right? So I'm going to go with this column. That's going to be the easiest choice because there's a bunch of 1s and there's some zeros. So this column is the easiest choice, okay? So again, since A21 is 0, the best choice to go down is either column 1 or row 2. No matter which row or column we choose, the determinant will not change. However, column 1 seems to be easier as both of the other entries are 1, whereas row 2 has a larger value in it, right? So for example, okay, so again, we're going to follow this formula here. So I'm going to do my first cofactor expansion. So my companion matrix tells me that this is going to be positive, and then I'm going to block out the entire column and row, and the submatrix that's left, the determinant of that is going to be my minor. So that'll be my first cofactor. Okay. So I start here because I'm choosing this row. This column, apologies. Going down this column. So I start at the first entry. My cofactor companion matrix tells me that it's positive. My minor, if I block out this row and this column, leaves me with this submatrix, 1, 2, 1, 3. Okay. And remember, the minor is a determinant. Okay, again, let's go back right here. So the minor, Mij, is the determinant of the matrix created by the remaining entries in A when I when I disregard all the entries in the row and the column of the cofactor that I'm trying to find. All right. So again, I start here. So I block out this column, this row, this submatrix determinant, which is 3 minus 2, or 1, is my Mij. So I have my M, and I have the sign. Okay. The sign for my cofactor here is positive, and that's easy to find from the companion matrix. My minor was 1. So my first cofactor is just a positive 1. Okay? Because positive, negative, positive, negative, positive, negative, positive, negative, positive. Remember, it just alternates in sign here. So my minor that's made, it is 1. I multiply that times a positive because of the companion matrix. So it'll stay, my cofactor will be a positive 1. So the minor is 1. The cofactor is also positive 1. Okay. So C11 is negative 1 to the power of 1 plus 1, or 2, times 1, which gives me just 1. So going down column 1 is going to give, so I'm going to do the second one now too, right? It's going to give me the determinant of A. Going down this row, this column, I'm going to start with the entry that's there. Okay, so again, remember you always multiply times your entry. Your entry times your cofactor. Expanded form is your entry times the sign in your companion matrix times the minor from that entry. So entry times the sign times the minor. Okay. So entry, which is 1, times the sign, which is positive because of the companion matrix, right? The position it's in, times my minor. This is negative, right? Because I'm going to the next entry here. So positive, negative, positive. So positive, minus, and the next one I have will be added. And so the entry, which is 0, times the minor. So again, I'm deleting this column, this row, and what's left over is 1, negative 1, and 1 and 3. Okay. But it doesn't really matter what this determinant is because I'm multiplying it times 0, so it goes away anyways. It doesn't even matter. Okay. So then my next one will be 1, and it'll be positive because it goes positive, negative, positive. So this will be plus 1. Okay. Plus, because of this sign, 1, which is the entry, times the minor that's formed. So if I block out this column, this row, this is the submatrix. 1, negative 1, 1, 2. 1, negative 1, 1, 2. So now I have 2 by 2, 2 by 2, and 2 by 2, which is easy to find the determinant for it. 3 times 1 minus 1 times 2. This whole thing is 0. This is 2 minus a negative 1. So this is 1 times 1 minus 0 times, this would have been 4, 3 minus a minus 1, but it's going to be 0 anyways, plus 1 times 2 minus 1, or 3. So when I add these together, I'm going to have 1 plus 3 is 4. Okay, so that's the cofactor expansion. So again, for 3 by 3, this could be a very, very fast method, especially if I have more than 1 0 in a row or column. Okay, again, I prefer to use that 3 by 5 matrix that I formed from my 3 by 3 for determinants. But this method is very, very good. It's actually the only method we have for when we have a 4 by 4 or larger matrix. Okay, you have to use this method. Actually, you can combine methods, but you have to use this method. Okay, so let's say we went down a different row instead just to prove a point and to get better examples. So let's say I went down this row, row 3, right? So let's say I chose a bad row. I didn't choose one that has a 0. So we're really doing this just so you can see what a different row expansion looks like. So here we did a column expansion. Row expansion looks exactly the same thing. It's just that instead of going down a row, down a column, you're going down a row. So here we're going to go down the 1, 1, 3. Okay. All right. So find the determinant of this matrix. I'm going to go down row 3 instead. So I'm just going to choose a bad row, right? So remember companion matrix wise, right? Sign wise, plus, minus, plus. Okay. So the first one I'm going to do is I'm going to take 1, and it'll be positive, and I'm going to block out this column, this row, and I will have this submatrix. So let's do this real quick before I even go down this road. Why don't you pause and go down row 3 and do the cofactor expansion right now, and see if we get the same thing out. Well, we already know what the answer is going to be. The answer is going to be 4, but I'm going to do this right now. So why don't you just pause it and then go down this. So, okay, on 3, 1, 2, 3, pause. Okay, and we're back. Hopefully you went through and you did this on your own. Even if you didn't get the answer right, that's fine. It's always important to try something and then, you know what I'm saying, have a reference for the proper method of doing it so you can adjust your mistakes and then not make those same mistakes later, right? So I'm going to start with this entry because I'm going down this row. So I'm going to start with 1. It will be positive, right? And I'm going to multiply that times the determinant of the minor that's left. So block out this column, this row. So I'll have the determinant of this, which is 2 plus 1. Okay. So we're just going to expand it right now. Okay. Then I'll go this one. This is negative. So I'm going to minus 1. I'm going to block out this row and this column. So the determinant that I'll have negative 1 being multiplied by is 1, 0, negative 1, and 2. Okay. Then I'll have 3. So remember, plus, minus, plus. So this will say plus 3. I'm going to block out this column, this row. So this will be the submatrix left over, 1, 1, 0, 1. Okay. And then now, remember, 2 by 2s are really easy to compute determinant-wise. So this will be 1 times, this will be a positive 3, 2 minus a minus 1 is 3, minus 2, because this will give me a 0, right? So this will be 3 minus 2 plus 3, because this will be 3 times 1 times 0. So when you get good at this, you can really just look at this and be like, okay, boom, 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 here's my values. So when I do a determinant, if you know, it's relatively easy, I can pretty much do it in my head without expanding things out. Now, I don't want you to get in that habit yet. I want you to write everything out. Obviously, I'm a big stickler for you guys showing your work. Okay, but you should be able to get to the point sooner or later where you're like, okay, this is going to be 1 times 3 minus 2. So that's going to be 1 times 1, then 0. So I have 1 so far, and then I'll add it to 1 times 3. So 1 plus 3 is 4, right? So if I were going down this column, for instance, I could do that in my head relatively easy because I have a bunch of 2 by 2 determinants to find being multiplied by 1s, right? So it makes it pretty easy. So again, this is going to give me 3 because I have 1 times 2 minus a minus 1. This is going to be 2 because it's not minus 1 times 2. This is nothing, right? So I don't have to worry about it. Plus 3 times 1 times 1, or plus 3. So I'm going to have 3 plus 3 is 6, minus 2 is 4. The exact same value, okay? So when we have a large matrix, when we can use cofactor expansion alone, this should be we, not when. Okay, so when we have a large matrix, we can use cofactor expansion alone or cofactor expansion along with our 3 times 3 multiplication method that I showed you way in the beginning. Okay, so let's see. Do I have an example of this? I don't know if I did. I did. Okay, so let's do a big example. Okay. So we have a 4 by 4. So notice when you go down any row or column, let's say I chose this first one. We're obviously not, because look, we have here 2 zeros. So I want to go down either row 2, or here, this is probably the first 2 zeros that you saw, or I want to go down column 3, because then I only have to do 2 expansions because everything else is 0. I definitely don't want to go down this one because I got a bunch of 4s everywhere, right? This one is okay, but then I'm going to have a very long expansion when I do, because I'm going to have 4 different expansions. So definitely column 3 or row 2 is the best option because they both have 2 zeros. But let's say I went down this one, for instance. Okay, just to start it off, because that's where we started off last time. If I start off here, I would have 1. It would be positive, okay? And so the minor matrix I would have, if I delete this row and this column, is a 3 by 3 matrix. So now what I can do is, for this 3 by 3 matrix that I have to find the determinant for, right? It's 1 times the determinant of this. I can then go down this submatrix with another cofactor expansion. So I can do a cofactor expansion, another cofactor expansion, right? I can find the determinant of this submatrix by cofactor expansion and multiply that times 1. And that's fine. There's nothing wrong with that. But for me, I feel like it would be much easier to do my multiplication method where I take this 3 by 3 matrix and then I just repeat those 3 values, those first 2 columns, and I do that multiplication across the diagonals, right? So I can mix cofactor expansion with the multiplication method, right? So you can really mix any method of finding the determinant together with any other method, right? Now, I will say I don't mind personally doing multiple cofactor expansions, especially for this one, right? If I use this one and then the cofactor has this minor, I could choose this column to go down in the submatrix because there's 2 zeros here, and I would only have to do one, where I can delete this row and this column and have these 2 things as my determinant, which wouldn't be too bad. That would be 1 times a -4 plus 1, right? So that would be 3 for my first one. 1 times 3 would be the first thing, and then I would continue down. And that's not too bad, right? But I do this a lot. I feel like it's much easier to mix together the cofactor and the 3 by 3 methods. So let's go ahead and do this, okay? Like for reals, instead of me doing a lot of literally hand waving, right? Let's do some actual math. So if I want to do this, I have 2 choices. So again, row 2 or column 3 seem to be good choices because they both contain 2 zeros in them. So let's go ahead and choose this column 3 in this case. All right, so if I choose column 3, so remember it goes plus, minus, plus. So this is positive. So it's +1 times the entry that's there. So it'll still be a -1. Okay. And if I delete this row and this column, I have these and this as the submatrix. So 0, 1, -1, 1, 1, -4, -1, -1, 1. Okay. So again, it stays negative because it goes plus, minus, plus. So I have a +1 times a -1, which keeps it negative. When I delete this row, this column, this is the sub-matrix entries that I have. Again, maybe you want to do this on your own and pause it right now and then check back to see if you get the same thing that we're going to get. So maybe pause it in 1, 2, 3. Hopefully you pause it. Hopefully you tried it yourself. Let's see if you guys got the same thing. So again, this is what we have for the first one. Okay. This will be 0. This will be 0. So I don't even have to do this, right? Because remember, you have your entry times your minor, right? Times the sign in the companion matrix. So since I know I'm going to have to multiply those things times 0 anyways, okay, I don't even have to worry about even writing them out. So I know I did in this previous example over here, I actually wrote it out. You don't have to write it out. We already know it goes to 0. Don't even waste your time with it, okay? So I know it's going to go to 0, so I don't worry about chopping out these rows and this column and this row and this column because they'll multiply by 0. So I go straight to the last one, okay? So remember the way it goes. If it was plus, minus, plus, well, then this is plus, minus, plus, minus. Right? I can even go down this way because remember, plus, minus, plus, minus. So if this is minus, minus, plus, minus. It works either way. I have to subtract this value. Okay, so it'll be -1 times the minor from deleting this column and this row. So it'll be -1, determinant of 101, 111, 4, -1, 4. Okay. And again, now from here, I have to find these determinants. So I can go all the way back to this method and pick a row or column and do another cofactor expansion for both of these. That's fine. I can go down this row or this column since there's a 0 here, or I can go down this column or this row, and I can cofactor expansion this and multiply everything times -1. And I can cofactor expansion this and multiply that result by -1 as well, and then, you know, add those together or find this value and subtract it from this value. That's fine. Or I can do my 3 by 3 method for this one and this one, which is what I'm going to do, because that's what I was saying I like to do in this example. Okay, so from here we can use the 3x3 method or do another cofactor expansion to finish finding these minors, right? The determinants here are our minors, so we can do these determinants by either cofactor expanding them or the 3x3 method. So I guess we'll do both. Okay, I guess I forgot that I did that. So to do another cofactor expansion, let's go down column 1 for both parts. Okay, because again, 0 here and there's a 0 here, mixed with all ones, although it's the same thing as if I had gone down this row as well. I still would have a 0 and 1s, 0 and 1s. So we're just going to keep it easy and just go down the columns. Okay, so let's go down column 1 for both parts, because both of those have a 0 and all 1s. So hopefully you did this already. Okay, so I'm going down here, so you're not going to be able to see it because I'm on the next page, obviously. So the 0 I don't have to write, but this 1 will be negative. Remember, positive, negative, positive. So I'll have a negative here. Delete this row, this column. This will be the submatrix 1, negative 1, negative 1, 1. Okay. 0 goes away. Then it goes minus 1, negative 1, negative 1, 1. And then from here, so that's the 0. I didn't have to do anything. It's just there. Minus 1. Take out the row. Take out the column. You saw the subdeterminant we had. Plus, right? Plus a negative 1 will give me a negative 1. Take out this column. Take out this row. This will be the subdeterminant I have for this cofactor expansion. Okay. So that's what it will look like. All right. So now that I have that, that is just the expansion of the one. Okay, I need to expand the other one. I'm not going to calculate this value. I'm going to do sort of all one thing at a time on both matrices. So now I'm going to do the same thing here. Positive, so this will be negative 1 times this subdeterminant, a 0, and then another positive 1. Take out this column, this row, and this will be my next submatrix. Okay, so hopefully you guys have already done this and you're just checking your work at this point. Okay, so negative 1 times this entire cofactor expansion minus 1 times the entire cofactor expansion for the next one. So that first entry was 1. It was in a positive position. This was the submatrix formed. The next entry was 0, so I don't have to worry about the minor submatrix. The next entrance was a positive 1, and it was a positive companion entry. And this is the minor that was formed as well. Okay, so again, just so that we're on the same page. Okay, I have 1. Take out this row. Sorry, this column, this row. This was the submatrix 1, negative 1, 1, minus 4. Okay, 1, negative 1, 1, negative 4. When I take out this one, right, so positive, negative, positive, take out this row, this column, 1, 4, 1, negative 1 is what's left over. Okay, 1, 4, 1, negative 1 was what's left over. Okay, now that I have that, now I can actually do some math. I can do my 2x2 determinant methods and find out these values and just write out a nice long string of math. So I have negative 1 times my first 0, which I'm just taking away. I'm not even putting it in here anymore. Times negative 1. So this is 1 minus 1, or 0. Okay. Minus 1 times a negative 4 minus a minus negative 1. Right? So then that's negative 4 plus 1, so minus 3. Okay. On the next one, I have negative 1 times this again will give me same thing that was here, negative 3 minus 0 plus 1 times negative 1 minus 4, or negative 5. Alright, so now I got to do this math. So this is 0. This is a positive 3 times a negative 1, so I'll have a negative 3. This is negative 3 minus 5. Okay, negative 3 minus 5, which will give me a negative 8. So this will basically be 3 minus negative 8, or 5. Okay, negative 3 minus a negative 8, so that turns it positive. So that's 8 minus 3 basically, so that's 5. Okay, so that's my double cofactor expansion. Again, let's say I had a 5 by 5. I would have to do a bunch of cofactor expansions. Instead of doing it twice, I would have to do it like 3 or 4 times. Okay, so now let's say that we use the 3 by 3 method instead. So I would have my negative 1, okay, negative 1, and so for this determinant, I'm just repeating the first 2 columns at the end. I'll do the same thing here. I'll repeat the first 2 columns at the end. Okay. Okay. So I have my first one, and I'm repeating the last 2 columns. Okay. Then I have negative 1, and I'm repeating the last 2 columns. So again, the language I use to code these, it does not let me put the strike throughs through. I have to enter these as a matrix. Basically, I cannot put a strike through an entire column in a matrix. I'm sure that I can, but I don't want to spend, an hour researching how to do that for 2 seconds of a video, right? So you guys know how this works. We go across these main diagonals and we add them up. So this is going to be negative 1 times 0 plus 4 plus 1 minus 1, 0, minus 1. Okay. So again, 0 plus 4 plus 1 minus 1 minus, this is 0, minus 1. For this one, I have minus 1 times, the first one is a negative 4 plus a negative 1 plus 0, right? Minus 4 minus a negative 1 minus 0. So this is the math that I have. I don't know if you could tell, but already that was much faster to do than writing a bunch of cofactors out. But let's look at the math. So this is 4, this goes to 0, this is minus 1. So this is going to be negative 1 times 3. This is a minus 5. Actually, let's do this. This negative 1 and this positive 1 go to 0. This negative 4 and this negative 4 is 8. Times a negative makes it positive 8. So basically means plus 8 minus 3, which is what we had over here. Okay, which is 5. Much faster to do it this way. So this is always my preferred method, to do the 3 by 3 versus the cofactor expansion. But again, there are times where you have to do cofactor expansion. So you have to know both methods. This is a nice shortcut, right? This is not a traditional method that is taught. In fact, most linear algebra teachers that I know don't even teach this method, this 3 by 3 method. They only show you cofactor expansion. They never even discuss this 3 by 3. So I'm trying to give you guys a little bit of faster methods for doing some of the things in here, even if I don't tell you that this is a non-traditional method. There are quite a few non-traditional methods that we've taught, or that I have taught you in this class so far. Some quick runarounds, right? You could say. So let's go on to a theorem. This is actually a very, very important theorem. It has lots and lots of implications for the things that we've done already in this class. So if A is linearly independent, okay, meaning that the columns of A are linearly independent of each other, okay, they're, it's a linearly independent system, then the determinant of A is not going to be 0. Okay, so this is actually a very, very huge theorem, said very, very in a very, very short, condensed manner, right? So again, this is probably one of my favorite theorems of linear algebra because it has, again, a lot of implications. I have definitely seen this theorem downplayed in a lot of other classes. But if you have a square matrix and your determinant is non-zero, there is a lot of things that you can say about that. Okay, so I don't know if we're going to get into everything right now. I think we leave that for the next section, actually, where we talk about all the implications of this. But for right now, just know that if you have a square matrix and your determinant is not 0, then you are going to be linearly independent, which means you are invertible, which means that you now have a set of vectors that span Rn, right? It just goes into this huge list of things that are all true. Okay, so it feeds into that big theorem. So if I have an n by n matrix and I want to know if it's linearly independent or if it spans Rn or if I have an inverse, generally what I do is I don't do a reduced row echelon form. I don't go through all that stuff. I just compute the determinant. I use the determinant as a check for myself. If the determinant is a number and it's not 0, I know I have an inverse for that matrix. I know that the columns span Rn, and I know that my system is linearly independent. I can create any vector as a linear combination of those column vectors. I know that my linear transformation given by that matrix A is onto, that it is 1 to 1, that, right, just all these things come out from this small theorem. Okay, so it's actually a very, very important theorem. And again, I just use the determinant of A as a check for lots of other things, because the determinant is generally pretty easy to calculate, whereas going through and doing all your row operations by hand, even though I said at this point you can use a calculator, even if that wasn't the case, if you had to do everything by hand still, it can be very, very timely, whereas your determinant can be very, very quick, especially if you're 3 by 3 or lower, right? So very, very important theorem. Definitely understand this theorem and make sure how to use it properly, because it will save you a lot of time and pain and suffering. Okay, so let's kind of do a small not a proof, but just a verification of why this is true. Okay, so recall that if you have a 2 by 2 matrix, okay, then the inverse of a 2 by 2 matrix is given by 1 over AD minus BC, and then you swap these positions and you change these values. Okay, but notice, what is AD minus BC? That's the same as the determinant of a 2 by 2 matrix. Okay, so you have 1 over the determinant. If your determinant of A was 0, you would have 1 over 0, which is not possible, which means that you would not have an inverse existing. And that would mean that your A is a singular matrix, right? Meaning that there's no inverse possible. And if A is singular, then that means that it is a dependent system, right? Remember, if your system is dependent, you don't have an inverse possible. Okay, so again, all of those things feed into each other. So another way of talking about this is that if A has a 0 row or a 0 column, then you will have a determinant of 0. Okay, that's a quick way of determining whether or not you have a dependent or independent system, is do you have a row of zeros or not, right? And a lot of times, I've seen your guys' work, as you, in the last sections, when you were trying to determine whether an inverse existed or not using the A dash I method and reducing that down, if you end up in your end result with a row of zeros, right, then you knew that you had a dependent system, and then that your matrix was singular and there was no inverse. Okay, so if you have a triangular matrix, okay, triangular matrices, and in fact diagonal matrices as well, are super, super useful for finding the determinant, because all you have to do is multiply the diagonal entries. Okay, so if your matrix is upper triangular, lower triangular, or diagonal, then all you have to do to find the determinant is multiply all of the entries on the diagonal together. Okay, the product of the diagonal entries. So a quick example, I have this 4 by 4. I definitely don't want to do my cofactor expansion, because what happened last time Last time I had to do either multiple cofactors or I had to do a cofactor expansion for my 4x4 and then do my 3x3 method, right? Which isn't difficult, but it is a lot of math. It's a lot of arithmetic, as you guys have seen. So if my matrix is just a diagonal matrix, in this case upper diagonal, all I have to do is multiply the diagonal entries. So my determinant here is going to be 4 times 8 times 2 times 1. You say I left out the 1 here because it's 1. Who cares, right? It's 4 times 8 times 2, which is going to be 64, right? So you got 16 times 4 or 32 times 2. Either way, it's 64. Way, way, way easier if you have a diagonal or triangular matrix. There's not a lot of math involved, right? Compared to when that's not the case, right? So our next theorem, the determinant of A is the same as the determinant of the transpose of A. Okay, so if I were to transpose this, for instance, I would then have a lower triangular matrix, but my diagonal entries would still be the same, and I would still get the same determinant. So that's true not only for triangular or diagonal matrices, but for all matrices, right? That's just a quick, hey, look, we can apply that here really easily kind of deal, right? My next theorem is that if I have two n by n matrices, then the determinant of the product of those matrices is the same as the product of their determinants. Okay, so the determinant of A times the determinant of B is the same as the determinant of A times B. Notice this is not true for addition or subtraction. Okay, I can't throw an addition or subtraction in between here and say that they are equivalent. This property only holds for multiplication. Okay, I see students mess that up a lot. They think that, you know, A plus B is the same as the determinant of A plus the determinant of B. That's not true. It's only for the product of these matrices is the product of their separate determinants. Okay, and that's it. So the next section, we are going to go into more properties of determinants. We'll actually see another method for finding determinants, which is really combining all the stuff that we talked about before with this discussion of determinants. Now, so the big highlight of the next section is we're going to be doing reduced row echelon form in order to get our matrices into a triangular method or a triangular matrix, so that we can then calculate it very, very easily to find the determinant. Okay, so I don't want you to go through that method right now because there's a lot more to it than what I just said. I just outlined the basics of what's in the next section. There's definitely some smaller particulars you'll have to pay attention to. Okay, so see you guys on the next section.